Hello everybody. Today we will move from kinematics of the rigid body to the mechanics of the rigid body. But let us remind ourselves of what we are doing last time. Remember that we looked at finite rotations where we said there is a vector r which goes to r prime where r prime is equals r times cos of the rotation angle phi. So it's a capital phi here, plus n cap, where n cap is the direction of the axis of rotation, r dot n cap, into 1 minus cos of the same rotation angle capital phi, plus n cap cross the vector r sine of the rotation angle phi. So just to remind you, phi is the rotation angle and axis of rotation is given by n. And from this we also could write down the infinitesimal case. And we discussed that for finite rotation, the rotation can be written only by a matrix, but for the infinitesimal case, we can even write it using a vector. So r prime, because it's infinitesimal, I can just write this as r plus dr. And for infinitesimal rotations, phi is considered as d phi now, which is very small, so cos phi is just 1. So this term becomes r. Cos phi 1 means 1 minus cos phi 0, so the second term does not contribute. And the third term becomes n cap, or let me write it the way it will be easier. So this becomes minus r cross n cap d phi, because sine phi is just d phi now. This n cap d phi we could write as a vector which we called d omega, d capital omega, and then dr, which is r prime minus r, so this goes away, dr d phi then just becomes minus r cross n cap. We define the infinitesimal rotation matrix which is A. In case of infinitesimal, it becomes some I, which is the identity matrix, plus epsilon. Epsilon is the infinitesimal rotation matrix essentially. And this matrix now houses the three components of this d omega in the following way. The other three terms you can get by noting that this is antisymmetric. Now this can be written in an even interesting way. So let me just show you that. This can be written in the following way. I have n1. I define this matrix 0, 0, 0, 0, 0, minus 1, and 0, 1, 0. And with this, what comes when I define d omega, that is nothing but n cap d phi. So d omega I can write as, so n cap has three components. So this is n1 d phi, or let me take d phi outside common. So this is n1 x cap plus n2 y cap plus n3 z cap times d phi. Okay, so this plus n2, another matrix 0, 0, 1, 0, 0, 0, minus 1, 0, 0 times d phi, and there will be a third matrix. Let me generate a little bit of space for that. Plus n3 I need even more space. This third matrix is 0, minus 1, 0, 1, 0, 0, 0, 0, 0. If you look at the three matrices, they have one column and one row all 0, and the other blocks, like this one here, has off diagonal elements 1 and minus 1. That is the form that you have for all three cases. These matrices are called, usually written as M1, M2, and M3. And you can verify, if I use this, I will get back the form of the epsilon I have here. So this is not d omega, obviously. So this is something that I remind you of. So this is given by that entire thing. These matrices, so if I take the commutator bracket of MIMJ, which is essentially this will be epsilon ijk mk. So they follow this relation. Remember that for the Pauli spin matrices also we said that they follow the same relation. Now this relation has a name, it's called Lie algebra. So these matrices are the matrices which are called the infinitesimal generators of rotation. And in this case, they are in the special orthogonal form. Okay. And there is a huge lot of mathematics industry which lies on the Lie algebra. So if you wish, you can have a look at it. Let me also tell you a theorem without proving it. We saw that the displacement of a rigid body When one point in the body is fixed, is just a rotation about a given axis. We'll talk about now a more general displacement of a rigid body, and the theorem goes by the name of Chase's theorem. It essentially says that the most general displacement of a rigid body is a translation plus a rotation. So if you don't keep the one point fixed, as you did in case of the Euler's theorem, then you have to add that translation. So that's it. That's what I have for the rigid body kinematics. So let us now march towards the dynamics of the rigid body. Okay. To do that, let me first draw the picture of the rigid body once more. So this is one body, which is the rigid body. And say this is the origin of the space set of axes. And there is a point in the rigid body. And I define the body set of axes with respect to that point in the rigid body. And then you can think of a vector going from this point to that point. And if that point is the center of mass, then this vector will essentially give you the displacement. Okay. Now, as the Chase's theorem tells us that the most general displacement of a rigid body is a translation and a rotation, the translation will happen with respect to this vector r, and the rotation will happen with any vector that is centered at the, in this case, as we said, this, if we choose this as the center of mass of the rigid body, it can be any other point also. If we choose this vector to be fixed in the body, so this is a vector fixed in the body. So what do I mean by that? I mean the following. So I take a pencil and mark 2 points in the body, and the vector goes from one point to the other point. As the body rotates, the vector rotates with the body. So if I have any rotation of the body, the change of this vector will happen only because of the rotation of the body. If I have a translation, that vector will not change. The direction and the magnitude of that vector will not change. Remember that this is a vector which is not from the origin, this origin. So that vector will not change. It's not necessary for a vector which starts from the origin of the body set of axes for any other axis also. So I can define such a vector which is fixed in the body as a vector r as a difference of two vectors r and r1 and r2, and r1 and r2 can be any two vectors pointing at any 2 points in the body. And if these 2 points are kept fixed in the body, then this vector g just changes because of the body. So if I can write a change of this vector, so I get a change because of the motion of the body only. Because of the rotation of the body only. Let me write that here. On the other hand, if I consider the vector from there, so if I want to see the change in this vector with respect to the space set of axis, so let us call that dg space. That can happen because of the rotation, but that can also happen because of the translation of the, if you wish, the center of mass of the body. So this can happen because of the rotation. This can also happen because of the translation of the center of mass of the body. So this will be equals to a change of the center and the change of that vector with respect to the center. So what all we are saying is the following, that if this body goes from that position to this position, then if I would have considered that vector, this is either of R1 and R2 you can think of, then R1 has now, so this was going to this top, so let us level this, or let us give these colors so that you can identify them in the rotated frame, and 2 will suffice. Then this R1 prime is now pointing towards, R1 prime is the changed R, is pointing towards the same point, because we said that we have kept that vector G fixed with respect to the body. And this can happen because of two things. One is because this vector R has changed, and that is given in this term. And the other is because there is a rotation of this. So there is this rotation which has bring this point from there to there, and there is a translation which happened this way. So the translation is there in here, the rotation is there in here. Now, how much is the change because of the rotation? This is a change which we can readily calculate, because this I can consider as the change of the vector R1 minus the change in the vector R2, and this we have calculated here. The change in the vector R, which is dr, is given by R cross n cap d phi. So this is given by d omega, which is n cap d phi, cross R1 minus R2. And this is essentially d omega cross R1 minus R2 is G. So d omega cross G. So this gives us a very nice relation, the rate of change relation. So dg, any vector g dt with respect to the space axis, so change as calculated from an origin in the space set of axis, equals dg dt as calculated from a body set of axis, plus I write this as capital omega cross G. So we have defined, small omega as d capital omega dt. This d capital, sorry, this small omega is the instantaneous angular velocity. It's the rate of change of an angle omega, so it's obviously angular velocity, and it's instantaneous because of the following reason. First of all, okay, so it's also clear that it lies along n cap because the direction of omega is in the direction of capital omega. Small omega is in the direction of capital omega. There is one interesting thing here. The thing here is that, remember, we never defined any vector like capital omega. We only defined d omega. Hence, small omega, the instantaneous angular velocity, is not, and that not is very important, a derivative of a vector. This has to do with the fact that the finite and the infinitesimal rotations are quite different. So that we have seen in the previous day. There is no vector corresponds to a finite rotation. Omega would have given rise to a finite rotation. But there is a vector corresponds to an infinitesimal rotation. So there is a vector corresponds to infinitesimal angular velocity. So just let me show you where we defined omega. So we defined omega here, and there is no reference to. We defined d omega here. There is no reference to just capital omega. Okay. So this relation can be generalized now as a rate of change operator now. So anytime I have to calculate a rate of change with respect to time, with respect to the space set of axes, that will be the rate of change of time, rate of change with respect to time with respect to the body set of axes, plus the infinitesimal, the instantaneous angular velocity cross whatever is the vector. So this is a very nice mathematical tool that we have got, and let us start applying it directly. Where will we apply? Well, what is this going to give us? Let us see. So let's say that we are on the surface of the earth, and the surface of the earth, this earth is a rotating body. So this is, say, the equator, this is the north pole, and the earth has an angular momentum with respect to the north pole. So let me call that angular momentum as omega. So in the case of earth, omega roughly is constant. So over the year it doesn't change much, so we can consider it as constant. It does changes, the axis does changes over centuries, but we don't need to bother about that for small cases. Now, because this is rotating, when I am analyzing a motion here, say there is somebody moving this way, this is on a rotating reference frame. So this motions on the top of earth, So which means that all the motions that we analyze with respect to the earth sitting on the earth is with respect to kind of body set of axes. But it also means we know that the rotating reference frame is a reference frame which is, say, with respect to the center of the earth, is not inertial. Center of the earth, obviously, we cannot see. So there is one more reference system with respect to which it will not be inertial. There is a reference system which is fixed with the very, very far away stars. Very far away stars, they essentially doesn't move with respect to uh, the earth, and with respect to them, they can be considered, with respect to them, the reference frame on the face of the earth is not inertial. So not only center of the earth, also with respect to the faraway stars, the reference frame on the face of the earth is not inertial. So it's a non-inertial frame, which means that Newton's law will not be valid here. So there will be fictitious forces arising on top of the earth. So let us try to see what are those fictitious forces. Okay, for that, it's easier to choose the center of the earth, which is a hypothetical point for us because we have never seen it, as the reference of the space set of axes. So I get this, and let me uh, call this as only small s and this as only small b because that is easier to write. So I have ddt of, let's first look at what happens to the radius vector r with respect to the space set of axes. This will be just using the rate of change operator here, we get this, right? ddt with respect to s is ddt with respect to b plus omega cross r. Now we can define this as our vs, so the velocity with respect to the space set of axis, that will be equals to, we define this as v body, velocity with respect to the body set of axis, plus omega cross r. And then you want to calculate the acceleration. And that will be ddt of, the acceleration is calculated with respect to the space set of axis because there we know that the Newton's law will be valid. right? So I'll just put things into the operators and let us work things out now. First, this I define as the acceleration with respect to the space set of axes. This term breaks into two parts where I write ddt of, with respect to, this is Vs. Vs I can write as Vb plus omega cross r. So the first term I get is dVb dt with respect to body set of axis plus ddt of omega cross r with respect to the body set of axis plus omega cross Vs is again first Vb plus omega cross r. Okay, so in both cases I have written Vs as Vb plus omega cross r, which is coming from here. Now let's see what happens. So first term is As, which is the acceleration with respect to the space set of axis. This I define to be the acceleration with respect to the body set of axis, because the person who is sitting in the body set of axis will measure this velocity and the rate of change of that velocity, will call that as acceleration. Here the angular velocity of earth is fixed to omega, so this term boils down to omega cross dr dt with respect to the body set of axis is essentially Vb. So this term boils down to omega cross Vb, but I also have this term as omega cross Vb, so I get twice of that, and then I get omega cross r. Nice. Now you see, if I now write Newton's law, so some force is acting on this particle from external, so I call this F. If the mass of the particle is m, then so this force is calculated in the space set of axis, so this is this, which is equals m times AB plus 2 omega cross Vb plus omega cross r. So this is from, let's ask the question, what will the body set of axis observer infer? Well, what can be this type of force? So this type of force can be the force because of some gravitational force of some external body. Maybe a comet is passing by, so the gravitational force of that comet, if you wish, on a body on the surface of the earth. So what will the body set of axis observer will see? So body set of axis observer will think that Newton's law is correct, so this, he will write the equation this way. So this is, I call it apparent force, but this is the force that the body set of observer will infer. And what is this? So this already we can write from the previous line as equals to F minus 2 times m omega cross Vb minus m omega cross r. So these two are the extra forces which are not supposed to appear, but they are appearing because you are doing a transformation between two non-inertial coordinate systems. So these are fictitious forces. Why do I call them fictitious? Well, you see, if there is no external force, this F is 0, then also the body set of observers will see a force, which are these forces. So if I call these fictitious forces F fictitious, it has two terms. One is this, and this is Vb. Okay, you can identify this readily as the, what is this force? Well, think about it. This is just centrifugal. Simplest case, you can see m omega square r, where omega and r are perpendicular to each other, which may not be always, because if you see this picture, r can be some vector like that from our origin in the body reference frame, so it's not really perpendicular to omega. This force is always there. Because r is non-zero. If r is non-zero on the surface of the earth, and omega is non-zero because earth is not coming to a rest on spin, so that is always non-zero. But this force, if the body is stationary, NVSA, Vb is 0, this force doesn't contribute. So this contributes only when the body has a motion. And again, it doesn't contribute, its omega is parallel to the Vb, so this is not parallel to omega. Okay, when I say motion, I mean Vb. This force is called the coriolis force. Okay, and this is responsible for producing hurricanes and all, which you can all read up. I will not go much into the detail in the lecture. You can read this up yourself. Goldstein has a quite good discussion on this.